In this video, we are going to take a quick look at the idea of differentiating a power series in order to produce a new power series representation for a function. We're just going to do two examples in this video and then summarize because we're going to keep doing these kinds of calculus operations on power series for the next few videos. So just wanted to take a quick look at the main ideas here. What we have in this first example is a function that we know very well together with its power series representation. So we have 1 over 1 minus x, which we know has this power series representation where the terms look like x to the n. The idea is that we can differentiate 1 over 1 minus x. Its derivative is going to be a new function of x. Does that function, the derivative of 1 over 1 minus x, have its own power series representation? The answer is yes. And the power series representation we will get by doing term-by-term differentiation of the original power series. There's a concise way to do that, so let's see what it looks like for this example. The function that we would like to represent with its own power series is the derivative of 1 over 1 minus x. That derivative you can work out with chain rule and things like that is 1 over 1 minus x squared. So this is a new function that we have never written down a power series representation for. However, it's the derivative of this. So let's go through and kind of term by term differentiate the power series representation for 1 over 1 minus x. So we claim that this function has a power series representation that's going to look like the derivative of 1, that's 0, plus the derivative of x, that's 1, plus the derivative of x squared, that's 2x, plus the derivative of x cubed, which is 3x squared, and on and on. We can now write down a form for this power series because, let's see, we see this is like the constant term x squared. See if we can summarize this. I'm going to say that this is n x to the n minus 1 going from n equals 1 to infinity. There are other ways that you could write that so that you're indexing from n equals 0. Let me take a second now just to verify that this is in fact a form of this series, and then I'll explain why I wrote it in this way. Okay, so what happens when n equals 1? We would get 1x to the 0, so that's this first term 1. When n equals 2, we get 2x to the 1, so that's this term here. When n equals 3, we get 3x squared, and that's this term here. So you can see that this expression does match up with the expansion that we got when we did the term-by-term differentiation. The reason why I like this is because it looks like differentiating this with the power rule. So if I wanted to differentiate x to the n, I would say that's n x to the n minus 1. So that's exactly what I wrote here, n x to the n minus 1. But notice that when we took the derivative of the original power series, the derivative of the first term was 0. So it's like we lost the n equals 0 term. The interesting stuff started when n equaled 1. Okay, so to reflect the fact that when we differentiate the leading constant, it went away, our lower index is going to bump up from n equals 0 to n equals 1. So I think that this is the nicest way to present the derivative of this power series. Let's say what the radius of convergence is for this power series representation of the function 1 over the quantity 1 minus x squared. I'm going to do this kind of naively, but it turns out that there's a very strong statement that we can make that I will mention at the end. So let's go ahead and set this up. We can say that the radius of convergence we can determine by taking the limit as n goes to infinity of the absolute value of the ratio of the n plus 1th term to the nth term. So that's going to look like n plus 1 times x to the n plus 1 minus 1, so that's x to the n, divided by n x to the n minus 1. Some simplification here. This will be the limit as n goes to infinity of the absolute value of, how about I write the ratio n plus 1 divided by n times x. as n goes to infinity, this ratio n plus 1 to n, this fraction here goes to 1. So this limit will be the absolute value of x. For the ratio test, we want that less than 1. This tells us that the radius of convergence for this power series representation of this function is 1. That is the same as the radius of convergence for the original power series that we started with. That will always be the case. So when we differentiate power series, we keep the same radius of convergence. Before we go on to our second example in this video, I want to make a couple remarks here. There are two theorems that I just basically used, and that's what we will do in this class. It's typical in a college class on a power series to just use this information. That is that, I said this left-hand side equals this right-hand side, so let's just differentiate both and we'll keep the equality. But the thing is, this is an infinite sum. So is it the case that the derivative of the sum is the sum of the individual derivatives? Because that's essentially what I did here. That this works for power series is a theorem. So we will take it for granted that with the starting power series, you can just differentiate both sides and you get equality. The second theorem is that the radius of convergence remains the same. So going forwards, we will know that we can do this. In order to differentiate a power series, we will do this term by term differentiation, and we will keep the same radius of convergence. In the first example, we started with a known power series representation, and we differentiated it in order to generate a new function with a new power series representation. In this example, what we're going to do is look at the function f of x equals 1 divided by the quantity 4 plus x squared. And we have to recognize that as the derivative of something. So what is it the derivative of? Maybe I should anti-differentiate. Let's anti-differentiate 1 over 4 plus x squared dx. I'm just going to take a basic antiderivative here, so I'm going to omit the constant of integration and say that this has an antiderivative of 1 over 4 plus x. Let's see, that's 4 plus x to the negative 1, so negative 1 would drop down like that. Okay. Here I would like to focus on differentiation, and here I have anti-differentiation, so let me rewrite this. Maybe I'll do it plus c. Let me rewrite this so that we see how to proceed with the power series differentiation that we just did in our first example. Okay, so what I would like to say is that the derivative of the function negative 1 over 4 plus x is the function that we would like to find a power series representation for. So this is the derivative of negative 1 over 4 plus x. Okay. Now what? Well, this looks like our prototypical 1 over 1 minus x. We're going to have to do some adjustments here, but we can come up with a power series representation for this. Then I can differentiate to get a power series representation for this. So next step is to find a power series representation for negative 1 over 4 plus x. We are going to need to do some adjustments on this expression to put it in the classic kind of geometric series looking form. Let me factor a negative 1/4 in front. So we can say negative 1 over 4 plus x is negative 1/4 times 1 over 1 plus x over 4. But I'm going to write this as minus negative x over 4. Okay, this is a little bit messy. Let me clean this up. All right, so our denominator turned into 1 minus negative x over 4. This has the right form to do the conversion into the power series representation that we know for this type of function. Okay, so I'm going to leave that negative 1/4 in front and write that it's negative 1/4 times the series from n equals 0 to infinity of this expression raised to the nth power. So that's negative x over 4 to the n. We could actually now differentiate this and leave the negative 1/4 in front because that's just a constant times something that we would be differentiating. Is that what we should do? Maybe I'll go ahead and bring it all together. Okay, so let's take this one step further. You could do what I just said. You could do this 2 different ways and make sure you get the right answer at the end. You should. So let's do the sum from n equals 0 to infinity of negative x to the n. I'm going to think of as negative 1 times x all to the n. So that's negative 1 to the n, x to the n, times negative 1 from out here, all over 4 to the n times 4. I'll write this one more time, times x to the n. Okay, let me write it all the way back on the left now, and I'll put it in a little nicer form than this. So this is going to be the sum from n equals 0 to infinity. Negative 1 to the n times negative 1 can be thought of as negative 1 to the n plus 1. Similarly, the denominator will be 4 to the n plus 1 times x to the n. So that is the power series representation for this function, negative 1 over 4 plus x. Since the function we're interested in is the derivative of that, what we can do is now say that the power series representation for this function is the derivative of this power series representation. And again, that's a theorem, but we're just going to use it. So let's differentiate. We can now say 1 over 4 plus x squared has a power series representation that's going to start at 1 and go to infinity. Then I'm going to differentiate this term inside of our summation notation, and that really just involves dropping the n down and subtracting 1 off of the exponent. So let me write this, and then I will maybe go back and justify it a little bit more. Let's write out the expansion so that we can really see it happen. This will be negative 1 to the n plus 1 divided by 4 to the n plus 1 times n x to the n minus 1. That is the power series representation for this function. Let me just to fill in a little bit more detail because we're doing this for the first time in this video. Why don't I expand this just a few terms just so we can really agree that this is in fact the correct representation for 1 over 4 plus x squared. Okay, so here, if I start to expand this out, when n equals 0, it's negative 1/4. When n equals 1, it's going to be positive 1/16 x. When n equals 2, it's going to be negative 1 over 64 x squared, etc. Perhaps the most natural thing to do would be to now expand this. When n equals 1, we get positive 1 over 4 squared, so 1 over 16, times 1x to the 0, so that's just 1 over 16. When n equals 2, we get negative 1 over 4 cubed, that's 64, times 2x to the 1. When n equals 3, we're going to get positive 1 over 256 times 3x squared. Okay, that comes out of an expression we didn't see here. Let me write it. Okay, times 4 again, we get 1 over 256 x cubed like that. Okay. So these two steps I just did here were not necessary. I just wanted to show you kind of one more time the term-by-term differentiation coming into it. So the derivative of -1/4 was 0. We don't see that here because it's 0. And then the derivative of x over 16 was 1 over 16. The derivative of -1 over 64x squared is -1 over 64 times 2x. Then the derivative of 1 over 256x cubed was 1 over 256 times 3x squared. Okay. So I got this expression just by doing the derivative of this and understanding that I needed to bump that index up. But one thing I want to mention is that whenever you're working with series and you're trying to describe a series, maybe you're coming up with your final form for a series in sigma notation, it's always safe to write out the first few terms and make sure that they agree with your expectation. Okay, so this right here, after all is said and done, this is the power series representation for the function 1 over the quantity 4 plus x squared, which we were able to get to because we recognized that this was the derivative of something that we already understood, namely a variation of our classic 1 over 1 minus x construction. The only remaining question to answer is what is the radius of convergence for this power series representation? We don't need to do the ratio test or anything like that if we can go back and figure out what the original radius of convergence was for the series that we differentiated in order to get to this. For that, what I'm going to do is look at this. This piece is where I brought in a series representation based on my understanding of how this type of function behaves. So from this piece, this conversion into that geometric series form, we know that we are going to get convergence for x values satisfying the property that negative x over 4 has an absolute value less than 1. So for the radius, it's going to be the same as the radius of convergence for the original power series that we differentiated. So we need the absolute value of negative x over 4 to be less than 1. That's equivalent to the absolute value of x is less than 4. So the radius is 4. Okay, that wraps up this example, but we're going to keep doing these kinds of operations on power series. So I just wanted to look at 2 in this video. In a second, I will write down a quick summary. Okay, let's wrap up this video by summarizing the guiding principles behind the 2 examples that we just saw. Suppose we have a function f of x, which we know has some power series representation. Here I've written it in the most general form possible. So we could write it as Cn times the quantity x minus a to the nth power, where the Cn are the coefficients and a is the center. So if you start to expand that out, it looks like C sub 0 plus C1 times x minus a plus C2 times x minus a squared, etc. Suppose that this power series representation has a radius of convergence which is greater than 0. We're not interested in doing this if our convergence only happens at a single point. Then if we look at the nice open interval of radius r around the center, so that's the open interval from a minus r through a plus r, on this nice open interval, f is a differentiable function, and its derivative also has a power series representation, which we can write down based off of our ability to do term-by-term differentiation on our original power series. So in particular, the derivative f prime of x has a power series representation that's going to look like the derivative of this term, well, that's just constant, so that's 0, plus the derivative of this term, which is actually just going to be C1, plus the derivative of this term, that's going to be C2 times 2 times x minus a to the 1. And then if you'd like, let me write one more. The next one would be C3 times 3x minus a squared. Whoops, not equals, but rather we keep doing this. This is the expansion of the power series for f prime of x. We can write this concisely as the series where, let me write the terms first. It's going to be the original constants. So I'll write C sub n times this exponent, which came down. Notice that matches the subscript here. So n and n times x minus a to the n minus 1. So that is the form of the terms for the new power series expansion that we're getting for the function that we've created when we did the derivative of f of x. But we lost the c sub 0 term. So our starting constant happens when n equals 1. That's the power series representation for f prime of x. And the other result that we discussed and saw with one example is that this has the same radius of convergence. Okay, so I will leave this information here, but we are going to keep doing these kinds of computations on more power series.